Good morning, everyone. I'm Dengcheng from the Tianjin University. I'm honored to present our work titled Ladder at NSDI. I would like to express my gratitude to my collaborators, Xujing and Haoxu, as well as our advisors, Professor Jianrong Wang, Professor Xiulong Liu, Professor Keqiu from Tank Lab at Tianjin University, and Professor Mohammed Shahzad from the North Carolina State University, and Professor Guyue from the Peking University. Conventional blockchains, such as Bitcoins, rely on a linear chain structure. This design imposes scalability constraints because it requires sequential block generation, which becomes inefficient when multiple blocks are generated simultaneously, a situation known as a fork, where the blockchain divides into multiple branches. In contrast, a directed acyclic graph, DAG, a parallelized ledger structure enables the concurrent generations of the blocks, thereby overcoming the Bitcoin's throughput limitations. While block-DAGs improve the performance by enabling forked block generations, their increasingly complex topology introduces the three key challenges. First, transactions lose their natural ordering, requiring costly topological sorting. Second, without a stable pivot chain, nodes struggle to achieve the finality. Third, increased parallelism can actually weaken resistance to attacks, a crucial security trade-off. Therefore, in this paper, investigate to fully leverage the advantages of DAGs by optimizing parallel block processing, aiming to address the structural challenges we have identified and do so in an efficient and scalable way. Although several DAG-based protocols have been proposed to tackle these challenges, they continue to face the significant limitation in handling forked blocks. First, nodes must independently reconcile blocks and their processors. This results in redundant computation and inconsistent will across the network, causing significant confirmation latency. Second, the DAG's multiple fork nature complicates transactions confirmation. Even with the mechanism like spectral voting or complex referencing counting, the lack of a centralized fork resolution method prevents full utilization of the DAG's parallelism. Most critically, attackers can exploit the decentralized pivot chain selection to assume the competing chains, destabilizing the ledger despite exceeding the safeguards. These limitations continue to hinder the full potential of DAG system and form the core challenges our work aims to address. As we see, current DAG-based systems struggle with the handling forks. To solve these limitations, we propose a dual-chain architecture called Ladder. The concept is simple and powerful. One chain structurally constrains the other, creating the regular convergence points that impose the other on the DAG. All will maintain its parallel efficiency. As shown on the right, this diagram may seem complex at the first glance, but rest assured, in the following slide, I will guide you through your design step by step. While developing the ladder architecture, we faced the two major technical challenges that required careful consideration and innovation. First, we need to design a method where one chain could efficiently consolidate the forked chain from the other chain. This convergence mechanism has to maintain the structural integrity with significant parallel processing advantages. Second, we had to ensure that adversaries couldn't compromise the convergence nodes, a crucial security requirement to maintain the trust in the system. As I explain our full architecture, I will specifically demonstrate how we address these challenges. Let's start with the setup of ladder. Our system follows a delta synchronous network assumption similar to what Bitcoin Nakamoto consensus assumes. This time assumption provides both consistency and fault tolerance, even under some network delay. Additionally, we assume that the adversary contributes less than 30% of the total computational power, ensuring that security and stability of the system. Each node contains the 3 core components, as shown in the diagram: the client interface for submitting transactions, the verification module, and the transactions pool for processing, and the dual-chain ledger that stores the updated state. In ladder, each node can take one or more of the following 3 rules: upper chain miner, lower chain miner, and committee member. With these rules in mind, let me walk you through the overall architecture of ladder. Our system operates in rounds, with each round ended by the generation of the lower chain blocks. The upper chain, represented by squares, handle the blocks production, while the lower chain, shown as the circles, derives the convergence and narrows the width of the DAG. Miners participate in both chains simultaneously. 2 structure features are critical here: integrity preserving hash pointer, which maintain the consistency of the DAG, and the superblocks like the block L, which are used to handle special cases. This dual chain coordination forms our namesake ladder structure. Well, building on overview, let me present how ladder works in each round. First, nodes generate the blocks in the upper chain use the proof of work, POW. Then, based on the hardest chain principle, one branch is selected as the pivot chain, and its block producer becomes the standard upper chain block generator. These standard generators are then responsible for producing the lower chain blocks, which facilitates the convergence of forks. In this way, the upper chain enables parallel block production, while the lower chain, generated by the standard block miner, delivers the fast and reliable finality. Every lower chain block permanently orders all transactions, ensuring both performance and security. This simple yet powerful synchronization is what enables the ladder to outperform traditional architecture. To select the standard upper chain blocks, we introduce the hardest chain principle, as I described above. Unlike the heaviest chain principle used in Ghost, which counts the subblocks, the hardest chain principle introduces the dynamic difficulty weighting to enhance the secure parallel processing. Here is how it works. Instead of relying on the number of subblocks, the pivot chain is selected based on the cumulative computational difficulty of the entire subtree. Each block's difficulty, denoted as the dBi, is calculated using a formula that considers both the number of leading zeros in its hash, which we call the zBi, and the difficulty of all connected blocks in its subtree, represented by the set Si. This recursive approach ensures security while fully realizing the parallel blocks processing capabilities of the DAG. However, the lower chain cannot always guarantee the generation of a single lower chain block due to issues like conflicting the lower chain blocks or network delays. To address this, we introduce the superblocks. When the system detects the conflicting transactions or missing blocks in the lower chain, it triggers a Byzantine fault tolerance BFT consensus mechanism, which is deterministic. A committee of recent standard block producer is formed, with leaders choosing using a verifiable random function. This committee verifies, removes the invalid blocks, and generates a new super block in the lower chain, ensuring the finality and the maintained integrity of the ladder. During operations, ladder upper chain may encounter invalid blocks and forks. Let me focus on the fork resolution, where ladders elegantly handles two cases. While the tip forks were already discussed as a part of the standard hardest chain principle, where convergence nodes deterministically select a standard upper chain block in each round. Ladder also handle a second case, chain forks, where the blocks from the round R arrived too late to be included in the corresponding lower chain block BLR. In such cases, these late blocks are only recorded in the BLR+1, but crucially, they are never adopted as the standard upper chain blocks. With the structured coordination with the dual chains, both the tip and the chain forks are resolved deterministically. Like the upper chain, ladder's lower chain also deal with the two types of forks. For tip forks, where multiple lower chain blocks appear in one round, we are already introduced our committee-based super block mechanism, which ensures that a single lower chain is agreed upon. For chain forks, which happen when nodes diverge on block selections and produce the competing versions of the ladder. Ladder leverages the subsequent rounds and applies hardest chain principle to evaluate and converge on a single consistent ladder. Now let we walk through both the standard operations and the expansion handle in ladder. Let's turn to practical parameter settings. For the BFT committee size, as described before, superblock generation uses a BFT committee, but sizing is present as a key challenge. Since we are fundamentally proof-of-work based, we can't perfectly guarantee Byzantine nodes stay below BFT's crucial one-third threshold. However, our analyses show two probabilistic properties. The first one is, as the committee grows, the chance of the exceeding the one-third malicious nodes drop exponentially. Second, when the attacker's cumulative success probably reached 99%, the required number of rounds grew at a practical explosion rate. This creates an elegant secure scalability balance. Larger committee give stronger assurance while remaining optional feasible, as quantified in this table. Beyond the committee sizing, we also carefully designed the parameters such as the node incentive mechanism and the waiting time direction. Due to time limit, for more details, please refer to our paper. To validate our design, we implemented a prototype of ladder and conducted server experiments. We tested at homogeneous server conditions, maintain a controlled network latency of the 80 to 120 milliseconds across the 80 nodes, each equipped with 8 GB of RAM. The proof of work difficulty was set to 18, meaning that each node had to generate a hash with at least 18 leading zeros. To further assume that the efficiency of the ladder, we compared its performance with that of existing systems, including the Ghost, Inclusive, Pantheon, and Conflux. Our experiment results demonstrate ladder's significant performance advantages over the existing solutions, like the dark red line in the graph. Compared to Conflux results, ladder achieves 4,500 TPS and approximately 59.6% throughput improvement, while reducing the confirmation time by around 12.9% to 33 seconds. This experiment result was obtained through systematic testing across the 3 key variables: transactions volume per block, network size, and the difficulty levels. with throughput and latency as our core metrics. The data clearly show ladder's ability to maintain the superior performance while scaling under realistic conditions, typically of the blockchain systems. Our security analysis completely examined the defense against the symbol attacks, DOS, double spending, and eclipse attacks. Beyond these critical protections, ladder design fundamentally ensures the two blockchain essentials: security for valid transaction inclusion and availability for timely confirmations. We prove this through satisfied properties, including an innovative addition to the standard comma prefix, finality, and liveness requirements, with formal verification provided in 2 ceremonies. For further technical details, please refer to our full papers. Additionally, we extend our standard guarantee to the shopper for guidance. Finally, thank you all for your attention. Thank you very much.